Hi there everyone, welcome to another video tutorial. In today's edition, we will be designing and constructing a cardiovascular disease detection and prevention project. This project monitors essential vitals like glucose level, blood pressure level, body temperature, ECG levels, pulse rate and cholesterol levels in the body. All of these are displayed on a smart screen like the 20x4 LCD screen shown here. We will also be making the project to be Internet of Things based, where we will not only be able to see it on a dashboard but we can further analyze it and have a health professional remotely monitor and predict the health outcome of the patient. This remote IoT dashboard will be the ThinkSpeak IoT dashboard. In this tutorial we will go from the circuit diagram to how we breadboarded the components, down to assembling of the components themselves, to programming it, as well as testing it to ensure it is working as we need it to be. So without further ado, let us get into how this was made. Before we begin this design, we will take a route down the traditional way of doing this. We go to the lab to get the specimen's results on these parameters. The blood work of this person will reveal the person's cholesterol level, the glucose level, the blood pressure, the pulse rate and body temperature as well as the other things we needed in the project design. This traditional method, which is the invasive method, involves prickling the skin with needles and drawing blood samples. On these samples, various tests will be carried out and we can get the results and we can use these results to compare our non-invasive approach. The lab work will take some hours for the results to be out. But we will wait until they eventually come out. The process is a bit painful if you are not scared of needles. But it is frightening if you are. Hence why we are experimenting to find a better way, a non-invasive approach to cardiovascular disease detection and prevention. Once we get our results, as written here on this piece of paper, we move on to the designing the schematic diagram for the non-invasive technique. You can grab a free copy of the schematic diagram of this project by heading to the link shown below. You can read all about the circuit diagram there and its explanation. Make sure to download a copy of it too. Now, let us proceed to assembling the project design according to the circuit diagram. First, we begin the enclosure and how to mount the components and the modules in it accordingly. Already we have made openings to safely situate these modules in the enclosure. We begin with including the switch for insulating and introducing power to the rest of the components from the backup battery. After this, we mounted the LCD screen carefully under the top cover of the enclosure. Then we used the glue gun to apply some glue stick glues on the screen to hold it tightly in place to the enclosure cover. Once this was neatly done, we can proceed to the next thing on our to-do list. The next thing would be to glue the connectors that we will use to connect the sensors to the development board. Since we schematic diagram specified that we used an Arduino Uno board and a Node MCU development board. These 2mm JST male connector will house the female wire connector when we connect the sensors from outside the project enclosure design. And since these male connectors are soldered onto a Variboard, which we in turn solder a male jumper wire to it, so as to enable us connect it to the Arduino development board itself. The whole process is for ease and convenience of the wiring and connection is specified by the circuit diagram. Please see the schematic diagram in the link found in the description below. Now, we also glued the Arduino Uno board onto the base of the enclosed, but we also cut out an opening for programming the board itself. We have broken the circuit diagram itself into different parts so as to make very easy to connect them following the circuit diagram. Also, to make it easy when troubleshoot the design for any hardware errors or misbehavior when programming or testing it, we used a pair of lithium-ion rechargeable batteries which are rated 3.7 volts 3.8 Ah to power this project. They also act as backup power source when the design is not powered directly from an external power source. These LiPo battery holder will house the LiPo batteries themselves. Carefully apply glue to the battery holder base to firmly hold it to the base of the enclosure. Then proceed to glue it further to ensure it is strong and doesn't move when it is vibrated by mistake or intentionally. Once you are done with this, you can let the hot glue cool off and form a firm bond to ensure it is strong and firm. Since the Arduino Uno board and the Node MCU board needs 5 volts to work, we connected the LiPo batteries in series and used a DC-DC buck converter to buck the out voltage down to 5 volts so that it will be at a suitable voltage level for the development boards. Also, the comparator board for the ECG sensor is placed inside the enclosure while cutting out a through way for its jack plug-in. To make it accessible, we placed it in a vertical position. We needed to recharge the batteries whenever their power was depleted, hence we use a LiPo charging module which has a Type B charging USB port and we can conveniently charge the batteries when we want. This is also close to where the ECG sensor module jack port is located. Now we can proceed to regulate the output voltage for the modules and components connected in the design. Using a digital multimeter and setting it to voltage measurement, we can turn the knob of the onboard buck converter until it outputs 5 volts DC. This 5 volts would then be paralleled across the whole modules that are connected in the circuit diagram. Since this is the logic level all of them are using, except for the ECG sensor module whose comparative board uses a logic voltage of 3.3 volts. We can source the 3.3 volts level from the Arduino Uno board. Since it has an onboard regulator that can give us this output, we made a multiple output channel for this 5 volts logic using the female header pin soldered onto the Vera board where the modules and development board can be connected to it to get the 5 volts logic levels. Next we move to the connection of the LCD module. Since we are using a 4 bits method, we connected the LCD according to the schematic diagram. This means connecting the module to the Arduino Uno using male jumper wires. We connected the power rails first, then we connected the register select wire, the enable pin wire to the Uno board, then the 4 data wires from the Uno board to the LCD module. Once we are done with the LCD connection, we move to connecting other modules and ensure all the wiring are done accordingly. Like to ensure that this pulse sensor module shown here is properly connected and is also working. Enough about component assembly, let us move to programming the project design. Download a copy of the project Arduino source code that is in the description link below. Once you run the code, your serial plotter would be able to show you the ECG readings just as this one shown here. Also, when testing the pulse sensor and you open the serial plotter on the Arduino IDE, you can see the measurement taken as it is being plotted on the serial plotter on the Arduino IDE. Now we can really see what the pulse sensor is giving us graphically. Once we are done running the various codes needed for the vascular disease detection and prevention project design, we can proceed to actually testing out the project design to see if it confirms the results obtained from the laboratory lab blood work. We picked the same person that was used to obtain the lab results. This was very essential during the testing phase of the project itself. We connected all the sensors needed for the test to their respective ports. Once this is done, we are ready to carry out our non-invasive tests. Some of the sensors were custom made according to this schematic diagram and we attached them to a Velcro fastener to ensure we measure as closely as possible the reading we are looking for. Starting with the pulse sensor module, we attached it to the arm. The temperature sensor used to measure the body temperature was attached next to the person's specimen. We were going for a waterproof base temperature sensor using the Dallas DS18B20 sensor. We found out that the ordinary type works better as well. The cholesterol sensor module, which was custom made using the Beer-Lambert's principle, was attached to the thumb and ensured it was firm and strong. Next, is the ECG sensor. This has 3 sensor listeners and we place them accordingly to the positions on the body. These positions are to ensure accuracy of the sensor itself. Once these body sensor attachments were completed, we can proceed to powering on the device itself. On turning on the device, we are greeted with a welcome message, after which the screen clears and sometimes is taken for the microcontroller to ready the sensors. Once the sensors are reading, we can begin taking measurements and we can see each sensor reading on the LCD screen. Each line has what it is measuring and it is clearly stated there. Now it is time for us to send this data measured to an IoT dashboard. At first, we tried using the Cayenne IoT dashboard, but after setting up the dashboard, we found some inconsistencies and left it for ThingsPeak web server. The ThingsPeak telemetry provided us with the right avenue to quickly set up the IoT monitoring and remote analysis of the cardiovascular reports measured by the sensors, and that is it. We have successfully designed and constructed an IoT-based cardiovascular detection and prevention project design. Let us know what you think about this project in the comments section below. Thank you for watching and see you next time.